Deep in the scorched heart of the Sonoran Desert in California, just miles from the Mexican border, lies a massive agricultural operation that defies the laws of nature. Here, in a geological sink sitting 235 feet below sea level, where summer temperatures routinely breach 120 degrees Fahrenheit or 49 degrees Celsius, and rainfall is less than 3 inches a year, farmers are mass-producing alfalfa, a crop so water-intensive it is typically found in lush river deltas, not sun-baked salt flats. Hydrologists and engineers often view desert irrigation on this scale as a thermodynamic paradox. In this environment, the evaporation rate exceeds 3,000 millimeters per year, roughly 30 times the rainfall. Logically, pouring water onto this ground should leave behind massive deposits of mineral salts, rapidly turning the soil into a sterile crust similar to the desolate salt flats of the nearby Badwater Basin. Yet, satellite imagery reveals a shocking contradiction. Instead of a wasteland, space agencies capture a vast, unnatural geometric patch of emerald green visible from orbit. This is the Imperial Valley. Far from failing, this system has evolved into the most efficient biomass engine in the Northern Hemisphere. It generates over $2.6 billion in annual crops and delivers up to 10 harvests a year, while traditional farms in the Midwest manage only 2. How did 20th century engineers manipulate gravity to turn a saline depression into a biological gold mine? And why are global superpowers like Saudi Arabia and China quietly fighting to control the harvest from this specific patch of American sand? First, let's dive deep into the analysis of this geological phenomenon. To understand why engineers chose to farm in this hostile depression, we must look at the specific physics of the gravity gradient. The Imperial Valley sits inside the Salton Trough, a geological bowl that plunges to 235 feet or 72 meters below sea level. In contrast, the Colorado River, which originates far north in the Rocky Mountains, flows along the Arizona-California border at a much higher elevation. By tapping the river at the Imperial Dam, located 18 miles northeast of Yuma, Arizona, engineers utilized simple potential energy. The water naturally wants to fall downhill into the valley. This eliminates the need for massive, energy-consuming pumping stations, which typically account for 30 to 40% of operational costs in modern irrigation projects. However, executing this gravity-fed system required one of the most brutal construction efforts in American history, the All-American Canal. Construction began in the 1930s with a seemingly impossible task: moving water 80 miles west across the shifting, unstable sands of the Algodones Dunes, also known as the Imperial Sand Dunes. Engineers couldn't just dig a simple ditch. The porous sand would swallow the water instantly. To solve this, they deployed massive walking draglines, earth movers the size of buildings, to excavate over 60 million cubic yards of material. This is roughly equivalent to digging a tunnel from New York to London. Crucially, the construction involved creating a sophisticated intake system at the Imperial Dam. Here, engineers built 3 giant desilting basins. These structures slow the river's flow, forcing the heavy sediment to settle out before the water enters the canal. If they hadn't included this step, the muddy Colorado River would have choked the canal with silt within a single year. This fortified infrastructure was a necessary response to a catastrophic failure. In 1905, before the canal was built, a temporary wooden intake gate broke under the river's pressure. Without a proper control structure, the entire Colorado River changed course, pouring billions of gallons into the valley for 2 full years. This accident created the Salton Sea, which remains California's largest lake today, covering over 340 square miles, roughly the size of 5 Washington, D.C.s. The modern All-American Canal isn't just an irrigation ditch. It is a concrete-lined leash designed to tame a hydrological beast. Now, we arrive at the critical engineering problem. We have the water from the river, and we have the sunlight from the desert. But when you combine these 2 elements in a depression below sea level, you trigger a chemical time bomb known as salinization. To understand why this happens, we need to look at the chemistry of the Colorado River. As the river travels 1,400 miles from the Rocky Mountains, it picks up dissolved solids, minerals, and salts from the canyon walls. By the time it reaches the Imperial Valley, The water contains about 700 to 800 parts per million of salt. In a temperate climate, this wouldn't be a major issue. But in the Sonoran Desert, where surface temperatures hit 120 degrees Fahrenheit, the physics changes. When farmers flood a field, the pure water evaporates rapidly into the atmosphere, but the salt does not. It stays behind in the soil. Here is the brutal math. For every acre-foot equivalent to 325,000 gallons of water applied to these fields, approximately 1 ton of salt is deposited into the earth. With alfalfa requiring 6 acre-feet of water per year, a single acre of land accumulates 6 tons of salt annually. Without intervention, the soil salinity would spike within 3 years, creating a phenomenon called osmotic shock. This is where the salt concentration in the soil becomes higher than the fluid inside the plant's roots. Instead of the plant drinking water, the soil physically sucks the moisture out of the root system, killing the crop instantly. To defeat this invisible enemy, engineers had to build a massive, invisible machine beneath the dirt. This brings us to the technological marvel of the valley: tile drainage. If you were to slice a cross-section of an Imperial Valley field, you wouldn't just find dirt. 6 feet or 1.8 meters below the surface, you would find a vast, complex grid of perforated plastic pipes. This is the land's artificial kidney. The operation relies on a technique called the leaching fraction. Farmers here don't just water the plants. They intentionally overwater them by about 15% to 20%. This excess water acts as a solvent. It soaks down through the root zone, dissolving the accumulated salts and carrying them deeper into the earth. Gravity pulls this heavy, salty brine down until it hits the layer of tile pipes. The pipes collect this toxic liquid and channel it away from the roots, flowing into larger collector drains and eventually dumping it into the Salton Sea. Without this underground plumbing, which spans over 30,000 miles of pipeline throughout the valley, enough to wrap around the earth, agriculture here would be physically impossible. But the engineering doesn't stop underground. On the surface, precision is the difference between profit and bankruptcy. Because the system relies on gravity to move water across huge acreages, the ground must be perfectly flat. If a field has a slope variance of even a few inches, water will pool in low spots, drowning the alfalfa, scalding, while high spots remain dry and salty. To solve this, farmers utilize laser leveling technology. Before planting, massive scrapers equipped with GPS and laser receivers drive over the land. A stationary laser tower emits a rotating beam that creates a perfect reference plane. The scraper's computer adjusts the blade height hundreds of times per second, shaving off high points and filling low points with millimeter-level accuracy. This creates a dead-level surface that allows a sheet of water to slide across a 100-acre field like a glass table, ensuring every single plant gets the exact same hydration. Now that the engineering has stabilized the environment, we can unleash the biological engine. Alfalfa or Medicago sativa. Why alfalfa? Why not corn or wheat? The answer lies in the plant's evolutionary architecture. Alfalfa is not a grass. It is a legume with a superpower, a massive, aggressive taproot system. While wheat roots might go down 3 or 4 feet, alfalfa taproots in the Imperial Valley can plunge 10 to 15 feet or 3 to 4.5 meters deep. This allows the plant to access moisture reserves far below the scorching surface sand. But more importantly, alfalfa is a nitrogen-fixing machine. Inside the root nodules, a symbiotic bacteria called Rhizobium mellilodi converts atmospheric nitrogen into ammonia, essentially creating its own fertilizer. This makes alfalfa the perfect pioneer crop for desert soil, which is naturally devoid of organic nutrients. But the real reason alfalfa dominates this valley is its metabolic speed. In traditional farming regions like Montana or Idaho, the cold winters force alfalfa into dormancy. The plants shut down for 4 to 5 months, limiting farmers to perhaps 2 or 3 harvests a year. In the Imperial Valley, the furnace never turns off. The combination of intense solar radiation and unlimited gravity-fed water puts the alfalfa into a state of permanent, turbocharged photosynthesis. The plants grow so fast you can almost watch them rise. A field here is harvested every 26 to 28 days in the summer. As soon as the mechanical harvesters cut the crop, the water gates are opened, and the cycle restarts immediately. Farmers here achieve 8 to 10 cuts per year, producing yields of 8 to 10 tons per acre, double or triple the national average. However, this speed creates a unique logistical challenge. In most parts of the world, hay is cut and left to dry in the sun for a week. Here, the ground is so hot, often reaching 140 degrees Fahrenheit per 60 degrees Celsius, that the hay cures in less than 48 hours. If the farmers wait too long, the leaves, where 70% of the protein is stored, will become brittle and shatter, turning premium feed into dust. This forces a 24-hour industrial ballet. Huge fleets of swathers run at night to utilize the slight humidity, followed by balers that compress the hay into massive 1-ton export blocks. So, let's recap the mechanism. We have a river diverted by gravity, a field flattened by lasers, a soil flushed by underground pipes, and a plant that has been genetically and environmentally hacked to grow non-stop. It is a closed-loop industrial system that converts sunlight and river water into protein at a scale found nowhere else on Earth. Are you curious about how much revenue this project generates? Under the glare of floodlights, fleets of industrial swathers move in echelon formation across the valley floor. They harvest at night to preserve leaf moisture, processing this green gold at a speed that turns the reclaimed salt flat into a $2.6 billion annual engine. Collectively, this valley churns out over 2 million tons of hay every year. In the commodities market, this high-protein alfalfa is trading north of $300 per ton, making it more valuable per acre than wheat or corn. But where does all this biomass go? Domestically, this is the metabolic fuel for California's $50 billion dairy empire. The intense desert heat concentrates protein in the leaves, which maximizes milk production in the state's 1.7 million cows. In a literal sense, the glass of milk on a table in San Francisco was forged in the furnace of the Sonoran Desert. However, follow the supply chain to the port of Long Beach, and the story shifts from agriculture to geopolitics. Roughly 20% of this harvest is compressed into high-density bales and loaded onto container ships bound for China, Japan, and the Middle East. This trade reveals a controversial economic concept: virtual water. Take Saudi Arabia. In 2016, the kingdom banned the domestic growing of alfalfa to save their own dying aquifers. Instead, major Saudi dairy conglomerates purchased 15,000 acres of land right here in the American Southwest. By shipping this hay across the ocean, they are performing a masterclass in resource arbitrage. They aren't just buying animal feed. They are effectively importing the Colorado River. For every ton of alfalfa exported, approximately 150,000 gallons of American water leaves the watershed forever. The United States is acting as a hydration battery for the world, converting a shrinking river into a tradable global asset. But for all its economic glory, the Imperial Valley is operating on borrowed time. The very engineering that made this miracle possible is now driving an environmental catastrophe. The crisis centers on the Salton Sea. As farmers become more efficient, switching from flood irrigation to precision drip systems to save water, there is less runoff flowing into the sink. The sea is shrinking. As the water recedes, it exposes thousands of acres of dry lake bed, known as playa. This isn't just mud. It is a chemical time capsule. After a century of agricultural drainage, the sediment is laced with arsenic, selenium, and pesticide residues. When the desert winds whip across the valley, they lift this toxic dust into the air, creating poisonous storms that have given Imperial County the highest rates of childhood asthma in California. We engineered a way to flush the salt out of the fields, but we had nowhere to put it but the air we breathe. Simultaneously, the fuel source for this entire machine, the Colorado River, is running on empty. Upstream, the massive reservoirs of Lake Mead and Lake Powell are sitting at historic lows. Climate models predict a 20% to 30% reduction in river flow by 2050. The law of the river is breaking down. Urban centers like Los Angeles and San Diego are looking at the Imperial Valley's massive water allocation, which accounts for nearly 70% of California's share of the river, with envious eyes. The political question is inevitable. Is it sustainable to grow export hay in a desert when 40 million people are facing water rationing? So, can this model be replicated globally? Nations like Egypt and Australia are attempting similar feats, but the Imperial Valley has a unique geological advantage that is hard to copy: the sink. Without a natural depression like the Salton Sea to serve as a designated toilet for the salt, most desert irrigation projects eventually poison their own soil. The lesson of the Imperial Valley is a brutal one. It proves that human engineering can conquer the desert. We can use gravity and lasers to turn a hellscape into a breadbasket. But it also proves that we cannot engineer away the consequences. We defeated the heat and we defeated the salt, but in doing so, we created a localized ecological disaster that may eventually make the region uninhabitable. What do you think? Is the economic value of this food factory worth the environmental price tag? Let me know in the comments below. If you want to see more breakdowns of how humans terraform the planet, hit subscribe. Thanks for watching.